Good morning. Oops, I forgot to get my mic down. Good morning. I want to just get you going on this gas stoichiometry problem set and talk about a few things that will hopefully help smooth the way. Uh, you don't have to watch this entire video, but you can fast forward and dip into any part of this that is helpful to you as you're tackling the the assignment for tomorrow. All right, so the first problem on your problem set is this one. It's the aluminum reacting with oxygen to form aluminum oxide reaction. And they are doing this at STP conditions. All right. So in fact, the first two questions, numbers 1 and 2, are both STP problems. And so I'm going to give you a little hint, a little clue. You do not need to use the ideal gas law for the first two problems. So anytime they tell you that you're at STP conditions, please remember that we can assume that 1 mole of a gas is equivalent to 22.4 liters in volume. Okay, so that's how we get between moles and liters in these kinds of problems. Okay, so but before my cursor's going nuts here. Before we do this, I just want to really go back to basics and just take a look at this problem. Let me just redraw this. So 4Al plus 3O2 2Al2O3. Okay, so instead of 2 liters of oxygen, let's say that they gave you, 20 grams. And the question is, what is the mass of aluminum that would be reacted if you reacted 20 grams of oxygen? So just a little, you may not even need this, but I'll just offer this. If the name of the game is to calculate the grams of aluminum, then here's how you'd proceed. So 20 grams of oxygen, that's the given, right? And in order to get from here over to here, we need to multiply that by, you need to convert to moles, right? And so what's the molar mass of oxygen? That's 2 times 16, which is 32 grams. And then you would have to use the mole ratio, right? So this is where we need the mole ratio between the aluminum. It's a 4-to-3 ratio. So that'd be 4 moles of aluminum over 3 moles of oxygen. And then finally, in the final step, we would turn that into grams. And so you'd look for the atomic mass of aluminum, which is 27.0 over 1 mole. Okay. And and then you would just do this calculation, run it through your calculator, and then that would give you the number of grams of aluminum. Okay, so that's just a quick little review. Now let's clear the slate, and this time let's actually use the information as given. So this time, instead of 20 grams of oxygen, they're saying we have 2 liters. All right, so that's the given. So I'm going to go ahead and we just take what we're given and we put it over 1. But this time, in order to get this volume of gas into moles, do you remember? If we're at STP, remember the trick? So remember, 1 mole of any gas occupies a volume of 22.4 liters as long as we're at STP conditions. As long as we're at STP. Okay, so I can put 22.4 liters here. Then the next 2 steps are exactly like the ones on the previous slide. So it's 4 moles of, we're going from, so here's where we're starting, and we're going from there to there, right? We're going from oxygen over to the aluminum. So that's 4 moles of aluminum over 3 moles of oxygen. And then you do this. And let's see, what do we get? So you take 2 divided by 22.4 times 4 divided by 3 times 27. and I'm getting 3.21 grams of aluminum. Okay, so hopefully you're doing okay. All right. So again, watch out. If you have STP, then you can make use of this conversion factor, right? Okay, so that's one kind of problem. Now, I want to just take a little detour before we go to number three. So I'd like to take number three on your problem set and just kind of set it up for you, okay? But before we go there, I want to kind of step back and look at this whole process. I want to look at the strategy of solving gas stoichiometry problems. All right, so these are gas stoichiometry problems from 30,000 feet level. Let's look at this from a high level. All right, so obviously stoichiometry is going to be we're going to need that, and um, we're also going to need to be figuring out how many moles. So with any stoichiometry problem, the mole ratio is really the heart of it. So I just want to remind you that not just don't forget that a whole bunch of stuff. You know how to take the mass of a substance and convert it to moles, right? And you also know how to do the reverse. You know how to take like the number of particles of a substance, whether that's atoms or molecules, and you know how to get back and forth from that. Okay. Um, if you have if you have a gas and volume, the volume of the gas in liters, and you're at STP conditions, then we know how to go back and forth there, right? So there's all these entry points into the mole, and then finally there's the ideal gas law, right, which we've just learned. And so if you solve the ideal gas law for N, which is moles, right, then that's PV over RT. And this little gem, right, will allow you to go back and forth. Okay. So that's, don't forget these basic skills. All right. Now, let's take a look at number three. This is the combustion reaction of methane, right? Methane reacting with oxygen to form CO2 and water. Okay, we've seen that like 100 times. So here it says of 100 grams of oxygen. Okay, so I'm going to go ahead and label 100 grams is allowed to react with an excess of methane gas. All right, so apparently we have more than enough methane. How many liters? So liters of carbon dioxide. That's what we're going after. How many liters of carbon dioxide could be collected at a pressure of 525 torr and a temperature of 24 degrees Celsius? All right. Well, in order to solve for volume, we're going to need the ideal gas law because are we at STP conditions? So are we at STP conditions? And the answer is no, we're not. Because 525 torr is not equal, this is not equal to 1 ATM, which is standard pressure. And 24 degrees Celsius is not equal to 0 degrees Celsius, right? So we are not at STP conditions. So we have to use the ideal gas law. All right. Now, in order to, let's see, liters of carbon dioxide, that would be the volume, right? And then this guy is the pressure, and this guy is temperature. So we know V, we know T, and we know P. So if you take your ideal gas law, PV equals nRT, and you solve it for, oh, I'm sorry, I said we know V, but we don't. uh, and you solve it for V, okay, then volume is equal to nRT over P. All right, so we know the temperature, we know the pressure, Of course, we always know R. Do we know N? Do we know how many moles? And the answer is no, not yet. We do not know how many moles of CO2 we have yet. And that's this guy right here. So we got to know how many moles. If we knew how many moles of CO2, then we could just plug that guy right in here into the ideal gas law and plug in these other numbers, and we're home free. But first, you have to use stoichiometry to figure that out. Okay, so that's where these problems become, a little more exciting, right? Because they have multiple steps. So you're going to have to use stoichiometry along with this 2-to-1 mole ratio to figure out moles of CO2. That's the step one. And once you know the moles of CO2, then you plug that into the ideal gas law. All right, and then you're home free. So if you go back to the map, if you go back to this map, I think what you can, maybe you can see this from kind of a, very high level, that we have to use stoichiometry first. We have to use stoichiometry first. And then once we know how many moles, then, we're here, and then we can go to the ideal gas law, right? So this is a problem where we're starting here and then we're working our way this way. Okay. Finally, question number four. This one, it's kind of the opposite. They're telling you the volume of the ammonia, okay? And they're telling you the temperature, that's here, and they're giving you the pressure. So here, you do have enough information to calculate moles, right? And when you solve for moles, you should get PV over RT. And in this case, you're going to be solving specifically for the moles of ammonia, right? That's what you're going to be solving for, because this information, it's talking about ammonia, right? And so if you're collecting that much ammonia, then they turn around and they ask how many grams of hydrogen could be made. Okay, well, once you know how many moles of ammonia, then you just use stoichiometry to get to grams of hydrogen. All right. So if we step back to this crazy map, um, in this case, we're starting here. We're starting with the ideal gas law. We're going here to moles, then using stoichiometry to figure out how many grams of hydrogen gas. Okay. All right. So I want you to, give this a shot. And I have several problems uh, recommended for you, which are numbers 2, 4, and 5. Only 2, 4, and 5. Okay. All right. All right. So best of luck. Please email me if you have any questions. Oh, and also I'll be available. Let's see, I said between 12 and 12:15. So please tune in right after lunch if you have any questions, and I'm happy to go over anything. Okay, thanks.